a while. I've been out cruising Alaska for the last couple of weeks, and then missed another week before that for some reason. Should have missed this week. I don't really have time to do this. This is going to be a short one today. But thanks for coming. Ping your friends in. Good to see the regular staff here, including my friend Brian, who I know has been missing me since I introduced him to Clubhouse a month or two ago. Anybody's welcome to raise their hand as always. Benjamin always does on entry to the room, and I bring him up on stage. Anybody else is welcome to do that as well. And let's see what else to say other than hello to everybody. Shamash, we've been in touch recently. Ben and I were talking 5 minutes ago. You and I were talking, I think, yesterday. Good philosophy room on Wednesday. We'll get more information on your what's going to happen next week later on. But anyway, good to see you. Want to say hi?
Sure. Hello. Good to see you. I speak for both me and for my alter ego, and we're live on YouTube, so you're free to
Okay,
start whenever you want to.
very good. Go ahead,
Thanks so
Benjamin.
much. It speaks for me too.
He speaks for you too, man. That's
No, it speaks for me.
okay.
I
That's
feel like I might be his alter ego.
oh, that's interesting. This is just a furtherance of your new. Everybody's moving closer to you. Your
All the
opinion
time, every
thing, right?
day.
Yeah. Okay. Well, that's good. Whatever gets you through the night, Benjamin. That's what we say. And I don't know if Ben can talk. He says he's going to be driving, so we'll just see if he unmutes, but we won't make. Yeah. Hi, Ben.
I'm
Oh, you're in the Matrix. Is what you are. Yeah. We're not catching you, Ben. You're in bad cell territory. Not getting you. No, it's not working. I don't think you're even hearing me tell you that it's not
changed right
working.
now, but yeah, I'm here.
Oh, there we go. Oh, and then you're gone again. Anyway, we didn't hear any of that. Okay. Well, we'll anyway chime in when you like. Let's see. So once again, this is welcome to Bite of Physics number 88, 6 June 2025. The latest in a long, lengthening series of bites of physics, where we talk about well-established, accessible, hopefully factual, if not true. Shamash and I can get into that later on. We never talk about the truth here, but we do talk about facts. Those are kind of two different things, in my opinion. Well-established physics, and we try to present it at a slightly more rigorous level than you may have seen it before, but avoiding the cutting-edge stuff, which can only be presented in kind of a wow gee whiz manner, which is fun. It's always fun to hear about cutting-edge physics, but the fact is, even I am not generally competent to evaluate, let alone present at cutting edge physics level. So I just avoid that. I like teaching stuff in general, and and I think there's lots of fun stuff to learn about the most fundamental things. We've got Andy, hero protagonist, joining us. Andy, good to see you. You want to say hi? I know you never do, right? I never do. I never want to say hi, but hosts always say that. Anyway, I invite you to say hi.
John,
Good
since we're
morning.
just warming up and people are still coming in, can I ask you
Well,
a
hold on a
question about
second.
your
Let
work
me just
today?
get a hi from Andy because he did Mike. He unmuted.
I did. I thought I did.
Unmuted.
Hi and good morning.
Good morning. Go ahead, Benjamin.
I want to ask a physics question for my work today, just to prepare my mind. Uh, we're working on a project of microfluidics moving little droplets around. They happen to have DNA in them, but I think that's not part of the physics here. And it looks like we're moving them from pad to pad, the 1 millimeter scale, and using 200 volts to move them. Do you have any insights as to the physics involved?
Well, I don't think I quite have a full picture of the apparatus yet. I think
Okay, simple notion. There's a series of pads, 12 pads, about a millimeter in size, a millimeter apart, roughly square.
you apply a voltage and the drop jumps from one to the other. Is that the
Yeah,
idea?
yeah.
Oh.
Is
Well,
that,
I'm guessing polarization is probably involved.
Are they charged droplets?
don't know the answer. They
Yeah.
have DNA in them. Does that imply that they must be charged either because
No,
of the DNA or because they're going to be in
doesn't
water?
it doesn't imply that, and unless you've gone to some lengths to charge them, it's probably reasonable to assume that at some level this has to do with polarization, right? Polarization will generally cause an attraction because you get like charges closer to things and opposite charges further away. Polarization is a general attracting thing. So uh, now I don't know, does it always jump to the higher voltage or the lower voltage? That would be, I guess, a question. Do you have to apply the voltage in one direction to get it to jump?
Yeah, I don't know the answer to that.
Well, it seems to me you haven't done enough experiments yet then.
No, we're just at the beginning of working together on this project.
Okay, well, that's fun. Maybe you'll have more experimental results by the end of the thing here. I should mention
Oh yeah,
I am going to have a hard end here today at 11. I have a gig tonight, and I have to actually go to the gig place to drop some things off at. I have to be there by 11:30, so we have a hard end at 11. We'll only be here around. We'll be doing this for about, and fortunately, it won't take very long. It's a relatively short one. So that's what we're doing today. And maybe we should, for that reason, maybe we should just get into it. I wanted to talk. So this is another. Let's see. What else did I want to say? Well, I guess I already said it. I've been gone for a couple of weeks because we took a cruise up to Alaska. Went to Glacier Bay twice because we took kind of two halves of a divided cruise that ended at Glacier Bay and then Juneau, and then started at Juneau and then Glacier Bay. And that was kind of fun. Glacier Bay is fun to see. I was surprised to learn that 99% of the melting of Glacier Bay was finished by the early 1900s. And since then, it's been a little back and forth, probably more melting than not. But it's really kind of a stunning story of what happened to Glacier Bay between the 1700s and 1800s. And you can look it up and read about it yourself. But I was surprised to learn that. Anyway, that's neither here nor there. Let's get into it. I was listening to some flat earthers, as I often do, express some satisfaction at being able to hang globe earthers out to dry on their contention that the Earth's axis wobbles around. Because if the Earth's axis wobbles around, how on earth could, pun not intended, how could ancient people have built structures to indicate the times of solstices and equinoxes if the solstices and equinoxes move around, and yet those same structures work to this day? And I thought, oh, well, that's an interesting question. I thought about it for a few minutes and realized that the answer is because they are built to find solstices and equinoxes. And we'll get into that too. But along the way, what I realized was something I'd never really appreciated before, and that is that while we commonly say that a year is the time it takes the Earth to orbit the sun, it's not. The thing we call a year is actually 20 minutes shorter than the amount of time it takes the Earth to revolve one time around the sun. And so that's kind of the topic today. On slide 2, I just kind of give you that fun fact. It takes the Earth about 20 minutes longer than, quote, 1 year. And I put the 1 year in quotes on purpose. And I'll tell you a little bit about why here. Because I don't mean 365 days. I don't mean 366 days. I'm not talking about the difference between leap years and non-leap years. I'm talking about the thing that we call a year, long term. And that
Is there a
thing
precession
is
in
less.
orbit?
And it does have to do with precession. And it's, and if you know about precession, you know all you need to know that this is true. But so, as did I, but I never really put it together before. So I'm suspecting that other people, in fact, I have pretty good evidence that one of the smartest guys I know didn't put it together because he commented on a Facebook post of mine in a way that indicates to me that he was thinking about it kind of like I had been thinking about it. And when I explained it to him, I haven't actually heard back from him again. So I'm kind of eager to hear. Yeah, it may be, yeah, I'll just warn you, it's possible because this guy is the smartest guy I know. And he took issue with my statement. So maybe I'm wrong, but I don't think so. And we'll see. It'll be interesting to see what he has to say. Let's see. All right, good. So, so I don't mean 365 days. I don't mean 366 days. I mean the thing that we call a year. And so the question is long-term year. And so the question is, what is that thing that we call a year long-term? And the answer will
Wait, I'll give it a
emerge.
shot.
Yeah.
Give it a shot. It has to do
Yeah.
with uh, the temporal alignment of the equinox and the solstice. In other words, when the sun is at its lowest point in the sky and when it's at its highest point in the
Yeah.
sky, and that temporal alignment of those over time domains much longer than 1 year.
Well, it didn't quite follow that, but I mean, I think you basically nailed it. I mean, that is, we can all go home now because not that we weren't going to get to that pretty much immediately, but that's right. I mean, what it really is, the thing we call a year is, you can think of it different ways, but probably the best way to think of it is the time between successive vernal equinoxes. The vernal equinox has, for no particular reason, primary importance in astronomical kinds of observations. And what is the vernal equinox? It's the time when the sun, when the subsolar point on the Earth traverses from the southern hemisphere to the northern hemisphere. That's the vernal equinox. During the winter, during the northern winter, the subsolar point is in the southern hemisphere. That means the point you'd have to stand at to look straight up to see the sun is in the southern hemisphere. And in our summer, it's the opposite, right? The place you'd have to stand to look straight up to see the sun is in the northern hemisphere for 6 months around summer. And the instant that changes from south to north is what's called the vernal equinox. And the year I'm talking about is indeed the time from one vernal equinox to the next. Go ahead, Benjamin. Did you have something to say? It's out of you.
I wanted to ask what the adjective vernal implies, because
Oh,
I
it
feel
implies
people apply
spring.
it to me a lot.
It implies spring, but I don't know what it means. I don't know if it literally means spring or if it means something else. Maybe somebody knows. Maybe somebody can look it up because I'm not going to Google it right now. I don't even know if that's what you were asking, but what it means is the spring equinox, the March 20th-ish equinox. Okay, so let's move on to slide 3, just for a little orientation. I've shown you the orbit of the Earth here. There's a lot of things on this diagram. And currently, a lot of the things on this diagram are based on facts that are only true currently. And one of those facts is that currently, the spin axis of the Earth points nearly at Polaris. If you go south to north and continue, that spin axis points nearly at Polaris. And in fact, as we'll see, this is a truly remarkable thing. There is, every 26,000 years, this happens. And the spin axis never points at a star as closely, a star as bright as Polaris, as closely as it does to Polaris right about now. So it really is kind of a remarkable thing. There will be different pole stars in the future, but none of them will be as close to the pole, and only one of them will be as bright as Polaris. So it really is remarkable to have a bright star right there at the north celestial pole. Okay, perihelion currently occurs slightly after winter solstice. The Earth in this diagram is rotating in a counterclockwise direction around the sun. Winter solstice happens And then a short time later, a week and a half or so, 2 weeks maybe, afterwards, the Earth is at its closest point to the sun. That's also another nice counterintuitive point that the Earth is closest to the sun at the winter solstice. And I think that's a good question. I think everybody calls it the winter solstice, even though it's summer in the south. I don't know if they call it the winter solstice in the south, but they should, just to avoid confusion. As you can see in the diagram, at the winter solstice, the spin axis is pointed. I'm showing you kind of a representation of the equator on the, if you can zoom in on those little Earths, you'll see there's a little equatorial ring at the lower part of the Earth and a arrow pointing up, indicating the direction of the spin axis, and it's pointing kind of at Polaris as indicated there. But perihelion, the Earth's orbit is elliptical, and the closest it gets to the sun is slightly after winter solstice, happens about January 3rd. Draco, this is a thing that has become much more important to me recently in talking about aberration, etc. But it turns out it's important to know that Draco is at another pole, a pole that's arguably much more important than the celestial pole. Draco sits directly above the orbital ecliptic. When we say ecliptic plane, we mean the orbital plane of the Earth. Draco sits directly above the orbital plane. And when I say directly above, I mean kind of from anywhere in the orbit. Draco's a very long ways away. So in that diagram, I'm putting Draco I'm indicating Draco right next to the sun. But you should appreciate the fact that it's enormously far away. So in that diagram, it's like 150,000 miles above that sun there. And so it's directly above every one of those Earths. It's directly above every single planet in the solar system as far as that goes. It's just directly above the ecliptic plane. So that's the thing. And of course, Polaris is the same thing. Polaris is extremely far away. So every one of those pictures of the Earth has its spin axis pointing in the same direction, and that direction is toward Polaris all year long. It may not look like it in that diagram, but it will if you remember that Polaris is really far away in that direction. Maybe 150,000 miles. I don't know. I just picked that number, but it's a long ways away. Okay, and so another thing that's true right now is that the times between the equinoxes and the winter solstice are slightly less than the times between the equinoxes and the summer solstice. Anybody tell me why that is? I'm
Is
going to
it
wait
is
for
it
an
because
answer here. Yeah,
is
go
it
ahead.
because the sun is not at the center, so it's one of the focal points, and so there's more distance to be covered during the summer half of the cycle?
Um, well, so you're getting at it. That last thing wasn't right, but I think you're getting at
Well,
the
he's saying it's an
fundamental.
elliptical orbit. That's does the Earth have an elliptical orbit around the sun? I think that's the form of the same question from my alter ego.
Yeah, so I'm showing you the elliptical orbit there, and I'm even showing you where the perihelion and aphelion are. And I'm showing you with a little dotted line there what's called the major axis of that ellipse, which goes through the sun. The sun is, as Shamash said, at one of the focal points. And yeah,
When you say
so
one is
all of that.
longer than the other, do you mean that it's longer by about 10 minutes or that it's longer in like by
Oh,
3 days?
well, you can see I'm indicating there. It's about 89-ish, plus or minus 1 days from winter solstice to spring equinox. It's 93-ish days from spring equinox to summer solstice. 94-ish days from summer solstice to fall equinox, and 89 days ish again from fall equinox to winter. So you can see it takes, in other words, the solstices and the equinoxes don't divide the year equally. It is, as I said, less time between winter solstice and the equinoxes than there is between summer solstice and the equinoxes. And I haven't quite completely gotten the answer for why that is yet.
So isn't it the case that the Earth is farther away from the sun during part of the year and closer to the other, which is another way of saying elliptical orbit. Is this not
Yeah,
the answer?
that's right. And in fact, that's exactly what I mean. When I say perihelion, I mean the closest. That's what perihelion means, closest to the sun. Aphelion, which is indicated. I don't know if you're looking at the diagram. That may be part of it. The diagram has perihelion and aphelion and a dotted line indicating the major axis of the ellipse on it. And so you can see that in winter, the winter solstice occurs very close to the same time that the Earth is closest to the sun. So all
Is
that's
what you want to hear is what you want to hear is then because the Earth is closer, then it moves faster. This is what you want to hear.
yes, that's right. That's the main thing. You'll notice it also doesn't have to go as far to get from spring equinox to fall equinox, but the really important thing is that it's moving faster when it's closer. That's right. That's what is that? Kepler's. Which one is that? Is that Kepler's first?
I never know.
Oh,
I
that's
just
the
say
third law.
Kepler's.
That's the third law. Yeah, so that's basically the answer I wanted. It's moving faster at winter solstice because it's closer to the sun. Um, that's the main point. Okay.
Can I make a plug for Andy's game here? Andy has designed this
Oh
orbital
yeah,
mechanics game, and if people
and
want to play with it, Andy, you should put the link again.
definitely I was playing with it myself yesterday. It
It's
is
fun,
very
isn't it?
cool.
It's
It is
fucking
fun.
fun.
Yeah, yeah, yeah. Put your link in there, Andy, and we will plug it some more. I was playing around, I was zooming around in the rocket ship, merrily thrusting and rotating, and oh, that sounds bad. I shouldn't say that. Ben, did you have something to say? Sorry, you were unmuted there. Go ahead. Unless that was a butt unmute, a butt mic. Must have been. Okay, let's see. What
Yeah.
else did I want to say on that diagram? There was something else. Oh, the other thing I wanted to mention is notice Orion. I've placed Orion there. That's about where it is, but once again, what it is slightly below the ecliptic plane and a very long way off. So what I should have shown is that thing way off in the upper right, 150,000 miles if you want, and slightly below the ecliptic plane. It's one of the few constellations that we get a really good view of in the northern hemisphere, despite being below the ecliptic plane. If you're in the northern hemisphere, you may know that on a nice winter evening, November, December, etc., you'll see Orion in the evening sky, usually to the west, southwest, and then moving over and setting. And it's one of the most beautiful constellations, I think. I mean, other than the Big Dipper, it's maybe the most recognizable. Probably should be the most recognizable. The Big Dipper just is more famous. And it's interesting because we see it despite it being below the ecliptic plane. And in this diagram, you can kind of see why. If you zoom in on the Earth there at winter solstice and imagine yourself in the northern hemisphere going around and around that spin axis, number one, you can see that the sun, you should be able to kind of see if you have three-dimensional capabilities, of visualization capabilities, that the sun is pretty low in the sky because the Earth is tilted away from the sun. But the nice thing about that is it means that in the evening, when you disappear around the right side of that Earth, you have a nice view kind of downward below the ecliptic. So right now, Orion is a kind of a cool constellation because of the way where winter solstice happens. We get a really nice view of Orion in the winter evening sky. Okay, I think that's all I wanted to say there. Any comments or questions before we move on?
Comment in chat from Kevin. Vernal means spring, coming from the Latin vernalis, meaning of pertaining to occurring in springtime, something along these lines.
Okay, so it's pretty much what we thought. Nothing other than just a fancy way of saying spring, I guess. Good, thank you, Plutos. Let's see what else we got. Oh, once again, I'll invite anybody who wants. If you want to come up and participate in the back and forth, raise your hand. I or somebody else, one of my co-mods, will hopefully see it and bring you up. Let's move on to slide 4. So before we move on into the thing here, I want to give a little aside on gyroscopic precession and do a little teaching of the right hand rule. We've met the right hand rule before in a lot of these bites of physics. Excuse me for a moment. Frog in my throat. So I want to talk about it in the case of gyroscopic precession here. I think we've all probably at some point in our lives played with a top. You know that if you spin a top on the ground, it'll have that point that it's kind of fixed to the ground, but the top itself will lean, and then the top will kind of wobble around one way or the other. And you may not, probably don't have any obvious way of determining which way it will wobble. So that's what I want to give you here first. And this is a result of the fact that gyroscopes react in a counterintuitive way to the application of forces. If you've ever spun a bicycle wheel on an axis and tried to like change the axis or had any kind of a gyroscope and done this, you know this is true, that when you try to turn it one way, it ends up turning at 90 degrees to the way you wanted it to turn. It's a very weird thing. It's hard to get I would say it's almost impossible to get an intuition for what will happen, but you can figure out. And that's what we're going to do here. So in this case, this particular top, you see the way it shows it's spinning. It's spinning, I guess, in what we might call a counterclockwise direction around its axis. But I want to be really careful about saying counterclockwise here, because counterclockwise is clockwise if you look at it from the other side. So there's always kind of an obvious side to look at. And in this case, when you look at this, I think anybody would say, that's a counterclockwise rotation. But just be clear that if you looked at that from underneath, it would be a clockwise. So it's much better to have a way that doesn't suffer that disadvantage. And the way we do that in physics is to tape our left hand behind our back so that we're not tempted to use it. We pull out our right hand and curve the fingers of our right hand, and then we have our thumb, and we find a way to make our thumb point along an axis such that our fingers are curling in the direction of rotation. And I hope if you all do this with this diagram, you'll see that if you curl your right fingers around that axis in the direction that that top is indicated as rotating, your thumb will be pointing upward and to the right in the direction of O prime. So that's a first application of the right hand rule here. We say the angular momentum of that top is literally up and to the right, because when I say it's up and to the right, I have fully specified the orientation of the spin and the direction of the spin, up and to the right. Whereas if I say clockwise or counterclockwise, you don't necessarily know what I mean. Up and to the right with the specification of the right hand rule tells you what the spin of that top is. Now there's another thing going on, and that's the torque on that top. In this case, there's a gravitational force which, coupled with the upward force on the bottom of the top at its tip, its bottom tip there, makes that top want to fall, right? In other words, there's a torque that would, if it were able to do what it wanted to do, it would make that top rotate clockwise. And I'm going to say clockwise because when I'm looking at that top, it would fall to the right. And falling to the right is a clockwise kind of a rotation in that picture. But rather than calling it a clockwise fall, I'm going to call that a into the page torque. for the same reason I did with the angular momentum. If I take my right hand and I rotate my fingers in the direction that top would rotate if the torque applied to it were allowed to do what it wants, then that top would rotate counterclockwise. My fingers will go counterclockwise. My thumb will point into the page. So I say that the torque on that top is into the page. And when I say it's into the page, that's enough said. I don't have to say clockwise or counterclockwise. You know, if you understand the right hand rule, that that's what I mean. So the torque on that top is into the page. The angular momentum of that top is up and to the right. And the rule, the physics rule, this is the analog of what's called of Newton's second law for rotational motion, is that the torque is what determines the rate of change of the angular momentum. So you have an angular momentum up and to the right, a torque that's into the page, and that into the page will cause the angular momentum, the rotation, the spin, whatever, to change from being up and to the right to being kind of up and to the right and into the page. And if you do that same thing now at the new place it is, you'll get the same kind of thing. But what it ends up doing is always moving perpendicular to the current direction of the angular momentum and to the plane, the plane that's specified by the spin axis and that vertical direction. So it will always move along that circle, and it'll move around that circle as it shows with the precession of the top in what I will now deign to call a counterclockwise direction, even though I should really call it an upward direction. The precession of the top ends up being upward. The top will wobble into the page and then around behind to the left and then out of the page and then around in front to the right and then back into the page and so on. So we can actually determine which way that top will precess by going through that. That may seem like an awful lot of work just to get that answer, but that's how you do it. So
I have a question.
yeah, go ahead.
So precession is fascinating and very difficult to explain, I think. And I am wondering fundamentally, does precession require a force additional to the spinning object? A gyroscope, for example, precession, let's assume that it's sitting on a table and it has gravity pulling down on it. And that's like a third thing that's involved, that gravity pulling down on it in a
Right, there
particular
has to
way.
be a torque. It is the torque that causes the precession.
There has to be a third thing. So just an object, an Earth spinning in the universe somewhere alone would presumptively not precess.
That's right. That's exactly right. And
So
that's
the
a
Earth
really
is
nice
experiencing.
lead into the next slide, but go ahead.
So the Earth is precessing. Is the Earth precessing more because of the moon or more because of the sun?
That's a very good question, and it even more anticipates the next slide. I should have looked that up. And my guess is that it precesses twice as much due to the moon as it does to the sun, because the torque produced by the moon, I think, goes as the same way as the tidal force. The moon produces twice the tidal force that the sun does. And I think that it's the same dependence for the torque. So I think the answer to your question is that the moon is twice as important as the sun, but I'm not sure of that. But that's a great question. Let's move on to the next slide because that's a perfect anticipation.
One related
for it.
question, and then
Yeah.
I'll
Okay.
listen. Is the moon forever and always equatorially locked? Or does it live above the equator or below the equator, or does that change?
Yeah, the moon has the moon's orbit is inclined about 5 degrees to the equatorial plane. So sometimes for 2 weeks it's above it's in the northern. The sublunar point is in the northern hemisphere, and then for 2 weeks it's in the southern hemisphere.
And spends equal amounts of time above and below? I think it has
Rough,
to.
yeah, probably long term, almost has to be equal, I guess, but not
That
short term.
and that still produces a kind of consistent directional torque.
Well, so yeah, now these are all really great questions. If you really want to calculate the effect of the moon on the Earth, it's incredibly complicated because of that 5 degree angle, because of the fact that the orbit of the moon is not a circle. There's all sorts of things going on. The dynamics are just incredibly complicated. But to first order, it's enough that the moon is almost in the ecliptic plane. It's it's in the equatorial plane, so that's already 23 degrees inclined. Let me go on to the next slide to answer your question, because I think this really is the point. If you look at the Earth there, this is a much more complicated diagram than it needs to be from a really great source for anybody who really wants to get into the weeds on this, that I'll mention later on. But you can see there kind of an exaggerated oblate Earth spinning around its axis that makes a 23 degree angle to the vertical, to the ecliptic. The ecliptic there is horizontal. That's the plane of the Earth's orbit. And so, to a large extent, what happens is, certainly with the sun, I mean, the nice thing about the sun is always out there on the ecliptic. And when and the sun is always kind of pulling up. Well, I shouldn't say that. In the orientation that you see there, if you imagine, the sun. So suppose the sun is off to the right, then the sun is pulling down on the nearby bulge, and it's pulling up on the farther away bulge, right? The sun is off to the right. There's a bulge that's kind of above the ecliptic plane on the right, and there's a bulge that's below the ecliptic plane on the left. But the sun pulls harder on the bulge that's above the ecliptic plane because it's closer. And that means that the torque that it produces, it tries to orient the Earth such that the bulge is in the ecliptic plane. It's pulling that nearby bulge down, and yes, it is pulling the farther bulge kind of in the opposite direction, but that's not as big a force. The net force due to the bulges is a force that is trying to orient the spin axis perpendicular to the ecliptic plane, if that makes sense. The important point is that the sun pulls harder on the nearer bulge. And so you can just kind of consider that a net force on the nearer bulge, which is trying to orient the Earth with its bulges in the ecliptic plane. All of that is to say that there is an into the plane torque on the Earth in this case. What you might call a clockwise torque, but I'm going to call it an into the plane torque. And that into the plane torque then is what ends up making the actual spin axis precess. In this particular case, you'll see that since the torque is into the page, the spin, that omega vector that points in this picture, points up and to the left, that vector will, the point of it will follow that circle. Now, in this case, kind of the opposite direction of the one we saw on the previous slide. It will move into the page and then around behind to the right, and then out of the page, and then around in front to the left, and continue. So the precession in this case is a clockwise, as viewed in the diagram, or more properly, downward precession, right? The precession, my thumb, when I use my right hand to get the precession of that thing, my right thumb is now pointing down toward the bottom of that diagram. Okay, that might have been kind of a lot. Sorry about that. But the result, let me just say this, Shamash,
Okay.
and then so the result of that is that in this particular case, and I'm just telling you this, the torque is such. If you calculate that torque, you get pretty good agreement with the experiment and the Newtonian analysis. This is not a relativistic analysis. Is that the precession period, the amount of time it takes the spin axis to precess one time around that cone, is about 26,000 years. And as I say down there at the bottom, notice that 1 year expressed in minutes, 365 times 24 times 60 minutes, divided by 26,000 years, is about 20 minutes. That's a number that we've seen before. In other words, that precession of the fact that it takes 26,000 years means it takes 1/26,000th of a year for it to precess one little piece around that cone, and that little piece corresponds to the 20 minutes, and that is exactly where the 20 minutes comes from. I probably shouldn't have delayed you for that, but go ahead, Shamash.
Just a quick clarification. In the previous example, there was a torque produced just because of the way that the top was rotating. But here, I'm guessing that what F and F1 and the red one mean on the Earth are the result of the sun's push, right? Or is it the same thing?
Yeah. So that's right. I don't really want you to worry too much. This is a diagram that's intended to illustrate a more complete rendering here than I want to go into. I wanted it mostly just for the picture of the bulges, the picture of the precession cone, and the ability to kind of point to the fact that the sun, which is over to the right, is going to be pulling harder on the nearer bulge than it is on the larger bulge, just because of the inverse R squared dependence. That's a tidal force. And that the net effect of that is a clockwise or into the page torque on the Earth itself. Whereas on the previous slide, when the picture associated with the torque, with the top, the torque in that case is a result of the upward force at the tip from the support and the downward force of gravity acting at the center of mass, which is a little over to the right because of the way it's leaning. Does that answer your question?
Yeah, totally, yeah.
Okay, good. So let's look at the result of that. I've told you that it takes 26,000 years. Let's look at what that means by going back to the diagram that I showed you on a couple of slides ago. So I'm just repeating here the slide that I showed you at the very beginning. What's going on right now? Let's just wind the clock backward about 2,000 years and notice that in this case, so let's see, did I say that right? Yeah, right. So I said that right. I should have made clear that the diagram on slide 5 correctly shows the direction of the precession of that thing. It precesses in that direction around that cone. So if I look at what things looked like 2,000 years ago, the axis of the Earth was I have to rotate it in a no, I guess I need to stop here for a second. Think about the fact that Earth, I should have had an auxiliary diagram, I'm now realizing. If you look at the first diagram, the circa 2000 diagram, all of those Earths have their spin axis kind of pointing up toward us, but tilting a little bit, right? Tilting 23 degrees away from up toward us. That's what they're doing. And that spin axis is in the process of precessing around to the right. It's going to precess around to the right, and then eventually be pointing exactly the opposite direction and then coming on around again. Oh boy, I'm seeing how much I needed another diagram here. But if I wind the clock back 2,000 years, that spin axis was a little bit. Remember the let's go back to slide 5. On slide 5, we saw that looking down on that spin axis would be rotating in a clockwise direction. So if I wind the clock back on slide 6, I have to make that spin axis move a little more in the counterclockwise direction. That means it's going to point a little more in the direction that I show there, off to the left a bit from where it's pointing at present. And in fact, 2,000 years is about 1/13. Well, it's exactly 1/13 of 26,000 years. So the spin axis would have gone through about 1/13 of a full cycle. That turns out to be 27 degrees. So I'm showing you in the next slide there what things looked like at the year 0. The spin axis was now pointing about 27 degrees off to the left as it's precessing toward the right in its clockwise direction. That would be the direction at the year 0. And the result of that is that the winter solstice occurred later than it does now, right? Did I say that right? Oh, yeah, right. It occurs later in the orbit. The Earth is orbiting in a counterclockwise direction, in a direction that I might call out of the page if I want to use my right hand rule. The Earth is orbiting in a counterclockwise direction. And so the winter solstice would occur later in the orbit than it does now. Winter solstice, in fact, what would the date of winter solstice be? And that's the interesting thing, is that even though winter solstice now occurs at a different point in the orbit, it occurs in late December, because that's when winter solstice happens. Winter solstice happens in late December, period. And that's because the spring equinox occurs around March 20th. The spring equinox always occurs around March 20th. The winter solstice always occurs in late December. The fall equinox always occurs in late September. And the summer solstice always occurs in late June. It doesn't matter where that is in the orbit, because that's how we keep time. Time is kept from the spring equinox. And the spring equinox is kind of, by definition, for some reason I don't really understand, March 20th-ish. So even though these things occur at different places in the orbit, they're still the same dates. And so you would have seen, you notice, if that winter solstice is in late December, then perihelion must have been in early December. In fact, it would have been about 24 days earlier if you just work out the effects of that 2,000 year portion of a 26,000 year cycle. You get about 24 days. So perihelion in the year 0 occurred in early December. Aphelion occurred in early June. Now they occur in early January and early July, but back then they would have occurred at a different time, because it's not important when perihelion. People didn't know 2,000 years ago. Well, they did actually, but common person didn't care when perihelion and aphelion happened. What they cared about was the first day of spring, because on the first day of spring, you get your stereos out, you put them in the windows of your dorm, you party out on the lawn. All that kind of thing. What matters is the first day of spring. That's what people care about. The first day of spring now, back then, occurred at a different point in the orbit. But it was still the same date. And that's really the source of the thing we're talking about here. The fact that I still, when I describe this thing, I still get a little bollocksed up, because I'm thinking December 21st is the top of the ellipse there. But it's not, right? December 21st is when winter solstice happens. And winter solstice happens when the spin axis points away from the sun. And if the spin axis changes the way it points, winter solstice will occur at a different place in the orbit. And that's really that's the central point of the bite today. Let me go on to slide 7 just to kind of show you what this ends up meaning in the future. If I go 6,500 years into the future, that's 1/4 of the way through this 26,000 year cycle. So circa 8,500, or as one source I saw says, around the 85th century. I like that way of saying it. Somewhere around the 85th century, the spin axis will now be 90 degrees around that cycle. It's still making a 23-degree angle to the ecliptic plane, to the vertical to the ecliptic plane. Still making that same angle, fundamentally, basically. That varies too by a little bit, but we're not going to talk about that. It's still tilted off vertical by 23 degrees, but now it's tilted toward the right rather than toward upward. And another 6,500 years after that, the spin axis is now tilted toward the bottom of the page, not rather than the top of the page. So in the year 8,500, the spring equinox will occur at the place in the orbit that the winter equinox now, the winter solstice now occurs. 6,500 years from now, spring will occur at the same place in the orbit that winter solstice now occurs. Spring equinox will be very close to perihelion. And 6,500 years after that, it'll be the summer solstice that occurs at the place in the orbit where the winter solstice used to occur. Summer solstice will now occur pretty close to perihelion. And an interesting effect of that is that will make northern hemisphere summers be more extreme than they are now. So 13,000 years from now, in the 150th century, I guess you call that, northern hemisphere summers will be more extreme than they are now. In the same way that southern hemisphere summers are now extreme because they happen when the Earth is closest to the sun. Okay, and you can see, and you can imagine what happens another 6,500 years after that, and then another 6,500 years after that. We're back basically to the same situation that we're in now. I've also indicated on these two diagrams, and you have to really do some three-dimensional visualization to see this, but you'll notice if you remember where Orion was, Orion is still, the orbit is still the same orbit relative to space. Orion is still in the same position that it was. All the constellations are still look like they do. It's just that we see them at different times of the year, and we see some that we didn't see before. For instance, in the spring here, if you put on your three-dimensional visualization glasses, you'll see that from mid-northern latitudes, 6,500 years from now, Orion will be a little lower and in the spring evening sky rather than in the winter evening sky. By winter, it'll be gone. Actually, I shouldn't say that. Actually, you'll still, I shouldn't have said by, well, yeah, it depends. You have to think about the full rotation here, and that's a very hard visualization. But it is true, but 13,000 years from now, Orion will not be visible from the northern hemisphere because it is below the ecliptic plane. And in the summer, which it will be when we're out there, Orion will still be kind of on the night side of the Earth, but the northern hemisphere doesn't see much night in the summer. The summer doesn't last long. You don't see constellations that are below the ecliptic in the summer. So Orion will no longer be visible at all 13,000 years from now. So we actually see different parts of the sky as time goes on. Okay, lots of really thorny visualizations going on here. Let me just stop there for a moment. See if there's even any questions. I may have, I always bite off more than I can chew in these things, but questions.
I'm just realizing how mind-boggling this is,
Yeah,
and because the way we study it is that, oh look, here's the the position of the Earth, and here's summer, and here's winter, and they're just completely different. The seasons depend on the tilt of the axis, whereas the other stuff, the depends on how close and how far. The closeness and furthest farness away from the sun, they have nothing to do with the seasons. And we used to think, because every map we've seen is just mapping those positions to the seasons.
right. Yeah, no, I think it, and this is exactly the revelation that I had that kind of led to this, even though I knew all of the things all of the ingredients that go into this. I hadn't put it together to really appreciate the fact that we measure years not by how long it takes the Earth to go fully around the sun in geometric inertial space, but we measure it from vernal equinox to vernal equinox, or solstice to solstice, or whatever. If you measure it starting at any one of those important points, you'll get the same thing, but what you'll get will be a time that's 20 minutes shorter than the amount of time it takes the Earth to go one time around the sun. And that's just I thought that was a fun fact.
The other thing is that Christmas Day happens on the 25th, traditionally. And the story was that it was Sol Invictus Day, so the festival for the sun god in the Roman Hellenistic religion. And so I never understood. I assumed that they got it wrong by a few days, because in my
Yeah.
mind it's on December 21st. But then looking at your diagram, it says that they actually got it a lot closer than we think that they did. And so that's probably the reason.
Well, I don't think that's the reason. I think you're making a bit of a
Am
mistake
I?
there.
Yeah, maybe.
Yeah,
Yeah, I don't
I
know.
think so, because once again, I mean, Christmas is connected to all the pagan solstice. I mean, there's a reason for all those late December things, and that's because for whatever reason, it's always been the case that the thing we now call March 20th ish is the spring equinox, and that makes the solstice December. That makes the solstice late December. That's just a fact, right? If you decide that the vernal equinox is going to be in late March, and you're going to keep it there, which of course you're going to keep it there, because it'd be crazy to have the spring equinox march through the calendar. Of course you're going to keep it there. Then the winter solstice is going to be in late December, and it doesn't matter where the Earth is in its orbit. All that matters is what direction is its spin axis pointing. And the stars will be
So,
different, right? Yeah, go ahead, Logarith. Welcome to the stage.
oh no, 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 I'm no, I'm actually just uh flabbergasted by what you're saying. What I mean by that in a positive way, because I'm not like someone who's knowledgeable as you are. Um, where can I find your kind of work in terms of how
Well,
categorize or
well,
yeah,
I don't know
or
if
like
you.
how you estimate? Yeah.
So I haven't done much more where, I mean, I did do a few little scratch things on the side for this presentation. This is not my area. This is well-known stuff. And let me tell you, I mean,
Mm-hmm.
as always, what I end up in preparation for these things, I think, okay, I'm just going to put a few slides together, and then I start Googling myself, and I go down rabbit holes that you would not believe. And I can tell you, if you find any of this stuff interesting and maybe want to understand it better than I've been able to make you
Mm-hmm.
understand it, if you just Google on axial precession or precession of the equinoxes, or just precession, if you put precession and Earth and axis in there, you'll find some really fabulous articles. I mean, just the Wikipedia, I would say if you would
Hmm.
look at one thing, the Wikipedia page on axial precession is wonderful. It's got some great animations. It's very interesting, and then it'll be the beginning of a million rabbit holes. Go ahead.
I didn't even like that's why I was in the comments and uh I was I was saying like in the process of people who, you know, process like math in terms of how you ascertain the Earth's tilt and stuff like that, they use math. That's where I had to like bow out because now I have to understand the math in order to explain how the Earth is tilted in order to explain like the seasons and stuff like that. As far as I understand, right?
Yeah,
Um,
let me
mhm.
let me just say, well, at the very end here, I'll have a link to a page that nobody here is going to be interested in going through, but you might be interested in taking a look at just to get a taste of how truly astonishing the details are here.
Mm,
People that actually do this, celestial mechanics, etc., working on the dynamics of Earth's precession. It is a fantastically complicated, just inherently three-dimensional thing that you have to
mhm.
whip out some heavy duty math tools, vector calculus, to be able to deal with, and some of the diagrams there. I'll show just one diagram to make that clear. Listen, I'm gonna run on here because I've only got about another 20 minutes, and then I have to actually shut the room down, and I want to finish up here. But
Okay.
yeah, thanks for your comments. So let's move on to slide 8, where I now show the path of the North Celestial Pole. When we talk about the North Celestial Pole, of course, we mean the direction in the sky that the Earth's axis points to, the place in the sky that the Earth's axis points to. And and as we now know, that place moves around in a circle with a radius. This is now spherical geometry. The radius of that circle is 23 degrees. It's always 23 degrees away from the point in the sky that is directly above the ecliptic plane. That's called the north ecliptic pole. So in the diagram on page 8, I'm showing you the north ecliptic pole. That's the place in the sky that is directly above the orbital plane of the Earth, and it's in the constellation Draco. And Polaris is 23 degrees away from the north ecliptic pole, and it's a place on this circular path that the celestial pole traces out every 26,000 years. That's a pretty small diagram there. I'm sorry, so you might want to blow it up if you can, or maybe look later on on a laptop. But you'll see Polaris is kind of off to the left and a little bit above center. That in this diagram, the north ecliptic pole is right there. It's a really nice identifiable place. If you see the constellation Draco, it kind of sits right in the fold of Draco. And I've drawn the 23 degree, the collection of all points in the sky that are 23 degrees away from the north ecliptic pole. That arrow is pointing counterclockwise, and that is to indicate, you may remember we determined before that the north celestial pole rotates in a clockwise direction. That direction, of course, is clockwise. When you look down on the Earth, the axis will rotate in a clockwise direction. But we're now looking up from the Earth, so that clockwise rotation appears counterclockwise when it's viewed from underneath. This is once again another reason why it's much better to think of it in terms of a direction. The direction in this diagram is my thumb should point out of the page toward my face to get that rotation. That's the same thing you get to get a clockwise direction when looking down on the top of that. Anyway, too much too much to say. But notice the really interesting thing here is what I said before. Polaris is far and away the only bright star that's maybe I should say far away, but it is the brightest star that is anywhere near as close to that circle as any other. In about 12,000 years, Vega will be called the pole star, but it's a full 4 degrees away from that circle. Polaris is about a half a degree away from that circle. It is very close to exactly on the spin axis of the Earth. And we are living at a very special time. 1,000 years ago, it was nowhere near as close to the North Celestial Pole as it is now. And 2,000 years ago, that star Kochab, the one corner of the Big Dipper, was actually closer to the celestial pole than Polaris is. So it was another star in the Little Dipper, the Little Dipper, not the Big Dipper, the Little Dipper there, that would have been the pole star at that time. So we're living at a very special time. Even 300 years ago, when people were navigating the seas, Polaris wasn't as good a pole star as it is now. And 300 years from now, it won't be as good again. We are living at a very special time in history. You'll notice there is a star called Gamma Cephei in Cepheus. It's the star that's almost directly over to the left from the north ecliptic pole, very close to the circle. That'll be a very good pole star in about 1,500 years. But then it's slim pickings. There aren't any bright stars until maybe you get around 17,000, 18,000 years from now. It'll come by a kind of a bright star. There'll be other stars. They'll be called pole stars, but none of them will be as close or as bright as Polaris is. So we live in a special time. Okay. The last real slide I wanted to mention, I just wanted to mention astrology. One of the interesting things about this whole precession of the equinoxes is what it does to astrology. It's been about 2,000 or 3,000 years. As I understand it, the dates were fixed to, the dates and the constellations were not fixed in Babylonia. I don't know much my astrology. Maybe somebody knows better than I do. But I think the kind of fixing of the dates to the constellations, as I understand it, were done in ancient Greek time, so about 2,500 years ago, something like that. And there's been about a 1 sign drift since then, about a 1 month drift. 2,500 years is about a 12th of the full cycle, and there are 12 constellations, so that these dates have changed by about 1 month since the time of ancient Greece, since the time they were fixed. And so you'll see there the dates of the various signs, the periods that are assigned to the various signs, and you'll see in red above them the actual dates that the sun is in those signs today. And you'll notice that I show the sun's motion along the ecliptic plane in the 2 diagrams. One shows half of the cycle, the other shows the other half. If you look closely at that, you'll see the astrological signs. You'll see the times that the sun is in each one. And in particular, Aries, which is the sign that the sun used to be in, start to get into at the beginning of at the vernal equinox. The sun entered Aries, and then it was in Aries for a month. Today, the sun is in Pisces in the vernal equinox, and it's there for about a month, a little more than a month. So it's about a 1 sign drift. And pretty soon, it'll be in Aquarius. We will eventually, in not too long, be in the, quote, age of Aquarius, when the sun has moved 2 full signs backward in time, back so that what used to be March is now January. And you notice that that's because, this whole thing is because we don't care about where the stars are to determine the year. What we care about is is when the winter solstice occurs. And the winter solstice occurs at a different place than when the vernal equinox occurs. It occurs at a different place in the orbit than it used to. So that really screws up astrology. And one of the rabbit holes I went down pointed out that there is a thing called sidereal astrology. Sidereal is the name we give to things when you actually, there's a thing called the sidereal year. The sidereal year is the thing you probably think of as the year, even though it's not what we mean when we say a year. A sidereal year is actually the time it takes the Earth to orbit the sun. It has nothing to do with solstices. It's how long it takes the Earth to orbit the sun, and it's 20 minutes longer than the, quote, year. But there's a thing called sidereal astrology, which evidently constantly corrects for the precession of the equinox. I think that's kind of a fascinating. I didn't go down that rabbit hole, but that's a big rabbit hole that maybe some astrology buffs would be interested in looking at if you haven't already. Okay. Oh, and I also noted there is one constellation that the sun does go through and always has that is not an astrological sign. It doesn't spend a lot of time in it. It's called Ophiuchus. There are 13 constellations in the ecliptic path of the sun, but one of them we ignore for astrological purposes. And there's the dates that the sun is currently in Ophiuchus. It comes in, between Scorpio and Sagittarius, I guess. All right. So the last slide is just, as I said, getting into the
A few
weeds.
questions.
Yeah, let me just finish this up, and then we'll just open it up for questions for 10 minutes, and then I have to go. This is just a picture. It's from the same source as that previous one, and I've listed the source there. If you want to just look at something and get a sense of just how complex this topic is, you might just open that, look at it, boggle your mind, and close it up before your brain hurts too much. But this is a diagram showing that the actual motion of the axis is complicated. There are nutations, as they're called. The axis doesn't just precess; it also kind of bobs up and down while it's precessing. The ecliptic plane itself precesses due to interactions of the Earth with the other planets. The orbital, the major axis of the orbit of the Earth precesses, just as does Mercury's, which led to the one of the first tests of general relativity. All of these things are incredibly complicated results of all of the bodies of the solar system interacting with each other in incredibly complicated ways. So I'll just end it there, and Benjamin, go ahead.
The first question was about a symmetry breaker. We talked about the torque required for precession. That torque has to be somehow off axis. It has to ultimately try to swap the axis of the spinning body. And it wasn't clear to me how the moon has any breaks its symmetry. It seems like it pulls the Earth in all directions equally. That was the first question.
Because sometimes it's above the equatorial plane and sometimes below, you mean?
Yeah.
Right.
Yeah, but
I
maybe it
agree
doesn't
with
matter.
you. I agree with you. I don't think I understand that.
Cool. And did you say the period of time was like 65,000 years?
The total period is about 26,000, a little less than 26,000.
26,000 years. That's very cool.
And that was measured, by the way, by Hipparchus in ancient Greece.
Wow.
Hipparchus
Wow.
was an amazing guy. That's one of the rabbit holes I went
Hipparchus?
down.
Does
Hipparchus.
26,000 years have a name?
Well, I don't. I just call it the precessional period, the period of Earth's axial precession.
Oh wait, Earth's axial precession.
It probably has maybe it has a better name. I don't know.
Yeah, it needs a name. You know, a certain number should have names, more than just dozen.
Let's call it a solar yard.
Is it?
And since
Oh, wait, what?
Well, what are you? What was that, Andy?
I think he's
Were you
having
kidding?
fun. I think Andy's making jokes.
I
Oh, a
I was
solar
Hold
yard.
the
You're just
press.
okay. I get it.
Hold the press. Andy is getting his humor out. Very cool. Very cool. So since Andy piped up, I had a request for a bite of physics, the oil drop experiment, quote, quote, by Millikan,
Mm-hmm.
quote, quote, a very good experiment.
Yeah.
More interesting meta discussion about
About
science
experimental
and a very
methods and
personal,
analyses.
yeah, you know exactly
so
why Benjamin is
more
interested in this one.
more complicated than that. But Andy has personal experience with this, and
with
it's very interesting as
with the
well.
oil drop. Did you do the oil drop experiment in college,
He
Andy?
I
did. So
did.
Oh my God, that's a
I want
really
to
hard
request
experiment to do.
the
Oh, we
first
talked about this
co-hosted,
once. Sorry, go ahead.
We did.
but I want a co-hosted bite of physics with Milligan,
That
in quotes in the
that's a good
title
idea. I'll put that on my list.
with Andy. That's my personal request.
Yeah,
For
I
everyone listening, the goal of that experiment is to measure the charge of an electron, which is something I never thought I'd be able to do. And it turned out I wasn't able to do.
so you were right. Yeah,
Yeah,
I
but the
actually I
approach
don't
is really,
remember
really
if
original
I
and
don't
very cool.
I don't remember if I ever did that experiment. It was available, I think, as one optional experiment for students I had at one point. I don't remember. I can't remember if any. I designed a kind of a virtual experiment because I know how hard it is to do. I designed a computer, simulation of the experiment, which worked
Oh,
really well,
I
surprisingly
did that
enough.
in quantum as well.
Yeah.
Speaking
Anyway,
of Andy and Andy getting his humor on, solar yard is 26,000 years. That is almost precisely, remarkably similar to the amount of time before anybody publishes the data for quantum entanglement.
I I,
John,
I, I confess I didn't see that coming. Go ahead, Shamash. Let's
just
let's hear from you.
before you leave, because we
Yeah.
haven't typed this back. So, how is it that the people who built the Stonehenge could
Yeah.
still predict the solstice and the equinox and all that stuff happening?
Yeah, right. So I guess as far as that goes, so the point is, the question is, how do you identify an equinox? Well, you identify an equinox because the sun sets directly west, right, on the equinox. And so if you build a structure that points to the place that the sun sets on the equinox, it will always do that by definition, right? It is that's what that's when the equinox happens. It will always point to that, and that thing doesn't care where the stars are in the sky. That doesn't care
But
what
I reject
time
that
of the
definition.
doesn't care what time of the sidereal year it is. All it cares about is that day the sun sets due west.
No,
So if
that's
you
a
build that thing, it will always
circular
do that.
definition.
Sorry?
Circular definition. It's a circular
Well,
definition.
well, it is in a way. I mean, you're right. That's kind of my point. Is that we
Because west, by
define.
definition, is the direction that the sun sets in the
Well,
equator.
I shouldn't say. And okay, I shouldn't say by definition, right? The point is that on the equinox, the sun does set due west, not by definition. By
No, but you
definition of the
haven't answered the question.
equinox.
You haven't answered the question, because then how do you figure out where west is? Well, you just look where the sun sets on the equinox. That's not the answer. What you do is you figure out the solstices.
The
And the
what?
way you figure out the solstices is
Oh,
you calculate the solstices is. And the way you calculate the solstices is you monitor how low the sun goes. And if you have a cave, this means that when the light goes through the cave, which it only goes through like briefly every day, it will light up a little circle on the back of the cave, the size of the opening of the cave. And that circle will move to the left until it goes as far as it can get to the left. Then it will move to the right as far as it can go to the right. And if you identify the point in time or the point in space of the leftmost traversal and the rightmost traversal, the point in the middle, or the time of year when it's in the middle, is your equinox.
Yeah, well, you
and
always have, you
west
always
is simply
have,
where the sun sets on that day.
in terms of local time, local noon is always the time when the sun passes your meridian. How do you know where your meridian is? Well, it's where the sun is when it's halfway from sunrise to sunset, right? That's the meridian is the place the sun is when it's in the sky halfway, half the time from sunrise to sunset. That's always the case
Right.
ish, right?
And so you
And
can do the same for the
so you
equinox.
always know your meridian, and therefore you can follow the sun. You can ask, on which day was it lowest or highest in the sky when it passed your meridian, and you can do that. And then of course that
Yeah.
meridian. Once you know your meridian, you know exactly what direction is north and what direction is south. And if you know what direction is north and south, you know what direction is west and east. And when the sun sets west, that's the equinox, and you will
Ooh.
find that that's the same day
Oh, so you
that you
only need
have the
one
same amount of
day to
time.
figure out which direction is west,
Yeah,
because you can just identify where it came up and where it came down
that's right.
and
Yeah,
draw a straight line between the two of
to
them.
first order. It's complicated, right, by the fact that there's always topography on. I mean, few places you have a nice ocean on both sides of you, or so it makes it a little complicated. But fundamentally, you can do that. Yeah. Let's see. So Shamash, did that answer? I mean, I think the most important thing about that is just that if you build structures that determine the day on which the sun does something special, well, that's is exactly how we keep time in the first place. So it's not surprising that they still keep time correctly. Some people think you may know about the change from the Julian to the Gregorian calendar. The Julian calendar tried to do what we try to do now. It wasn't about them mistaking sidereal years for tropical years, as they're called. The Julian year tried to make March 20th happen at the same, on the equinox every year. They wanted that to happen. And therefore, they added leap days. But what the Julian calendar did was it had a leap day every 4 years, period. They didn't really know exactly how long a tropical year was. They did the best they could. They knew they needed a leap year about every 4 years, and so that's what they did. But it turns out that's too many leap days, and therefore, over the course of 1,500 years or so, it drifted off by many days because you need to not do a leap day every century, except that you need to actually do have a leap day every 4 centuries, right? So the Gregorian makes a slight tweak on the Julian, but they're both attempting to do the same thing, to keep the vernal equinox, on March 20th ish, for whatever reason. So that's the next question is why that, right? Why March 20th? I don't know if I really do.
It's
That's
easy to
really
detect from the ground, right? Because you can measure exactly the time between sunset and sunrise, and you can probably tell. Whereas
well,
the
but I mean,
longest
but
the
why
longest
not?
day would be weird to find, but
But
when they
why
are
not
equal.
call that? Why not call that January 1st? That's
Oh,
really my
they did.
question.
The ancient calendars, the
Did
the,
they?
the Sumerians, etc. They had that as the number one day of the year.
I see. So then
Yeah,
the question is why did the people with bad idea win? The bad idea was to make it
they
some
had
other
they had they
time.
had bigger swords, I think. It's just-
Yeah, no, actually I've intrigued myself. I need to know the
Wait,
answer to
when
that
does the
question.
good idea ever win? Isn't that remarkable when the good idea wins? It seems to me
Yeah.
like,
Hey, listen, you guys, I really do have to go. If somebody wants to start an after party, I will listen in, but I'm going to be in my
wait, but I want to
car and
challenge
doing
the
some
entire
things.
thesis before you go.
Hmm.
What if instead of being a constant procession, it the symmetry breaker is the relationship of the moon to the earth, and the fact that sometimes it's closer, sometimes it's farther, and there's a synchronous relationship creates a very slow clock in which we are currently in a right going procession because of the timing of the Earth's the moon's orbit and the Earth and the proximity of the moon, but that
26,000 years from now, we could be in a counter rotation because that cycle gets off. So how would you exclude that possibility that we're in a periodic adjustment rather than a
Yeah.
cyclical adjustment?
No, I see what you're saying, and of course there's always possibilities like that. But the nice thing about and the way these calculations always go is you always assume smoothing in the sense that things aren't going to be what do they call commensurate. So that you don't have something commensurate going on, such that you get the same kind of everything's going to smooth out and the longer you wait, everything's going to average out more and more. And by the way, just as I leave, I just realized the moon. The answer to the moon problem is this: the 5-degree inclination I mentioned before. I may have said it wrong. The moon's orbit is inclined 5 degrees to the ecliptic. So it largely does what the sun does in terms of providing a consistent torque that makes the same kind of precession. It's not 5 degrees to the equatorial plane. It's 5 degrees to the ecliptic plane. Okay, so it follows pretty much the same path in the sky that the sun does. Sometimes it's 5 degrees below the sun, sometimes 5 degrees above. And with that, I really do have to go. I'm sorry, guys. I'm not even going to play you out today. I really have to get in my car and run. If somebody wants to start an after party, I will join it. And if you don't, I'll see you next week. Thank you very much, and goodbye.